we had this thing about threads, and everybody was supposed to read the book and maybe do a little bit of work with the threading. So that's why I'm kind of thumbing through it now. Any questions about threads?
Oh, can you run that code that you're looking at right there? I couldn't get it to load it on mine.
Well, this code is actually in Blackboard. So it's actually a picture of the code. You know what I mean? So if
I
yeah,
copied it. Oh, okay.
yeah. So if you go to the book examples and you go down to chapter 13, then you will find the code, the same code. So for example, here is a digital clock label, which is presenting to you a clock. Now the clock is supposed to be running as a run job. Now this is a little bit peculiar. What he's doing here is he's saying that the run job runs every second, and it updates the text by calling date.toString. And so every second he sets the text to the new date instance, and that new date instance has a string representation which shows you the date and time. So it's coming up as a label on a display and is being placed into a closable J frame so that when you look at it, where do you suppose it went? Here it is. So there's several, you can see all these different labels are being updated separately. Let me see if I can expand it. Yeah, we got a lot of labels. They're all running as separate threads. And so that's, you can see it's updating here. Then it updates there and it updates, it lazy thread updates. There's a lot of threads here. So let's take a look again and see what's going on. I don't remember how many of these things I created. 400. Okay, so there's 400 separate labels. They're each running in their own thread. They each get updated every second. And it looks actually, when you make a new instance, it's not every second. Some are updating every 0 seconds. Some go update once every 400 seconds, right? This is a lot of labels, and each label has a different delay. So let's just do a couple or 4 labels. And 400 labels is a lot of labels. And so let's do 4 labels. 4 labels is better. Should run a little bit faster too. But now they're updating every 4 seconds. It's probably silly, right? 1, 2, 3, 4 seconds. So you can see they're asynchronously updating. So that's kind of cool. And so let's take a look again and see what's going on here with these labels. So the run job is actually a convenient way to implement the runnable interface. And what he does is he runs as though he's a thread that knows how to run itself. And when you do the constructor on the run job, what you get is an overloaded constructor that tells you whether or not you want to start it right away or wait, how many seconds in between each run, and the number of times that you want it to run can also be specified. A daemon is true if you want to exit when the main exits. Otherwise, it will continue to run. And so that's the default for the run job. And when you hit, all of these different interesting and wonderful, I will call them options for the run job, you begin to see that it's a rich environment in which you can proceed to do all sorts of interesting control over your jobs. So when you make a new instance of a run job, what you're really doing is you're providing an implementation of the run method, which then gets executed using a thread.sleep every so many seconds. And so here is an example of the run job where, let's see if we can get to the constructor. This is the number of seconds. This tells you whether or not you want it to wait when you start. This tells you the maximum number of times to run. And this tells you whether it's a daemon or not. So it's not a daemon, which means it should continue to run after the main stops. It's not going to wait. It runs every 9 seconds, 9,000 milliseconds. And let's see if this runs. Yeah. So we've created a bunch of these jobs, and they're running asynchronously with respect to one another. So now that you've read about the threads, you know the difference between multi-threading and multitasking, right? So when you're doing something like a multitasking operating system like this one, you'll see I have many tasks that are running, including Zoom. That's a separate task. Each task has its own separate memory. And switching from one task to another has a lot of overhead because of the fact that each task has protected memory. So the Firefox can crash, but it won't impact Zoom, for example. The end of that sentence is we hope. So as a result, we are limited in terms of the total number of processes that we can run. In my case, I have 275 processes, but the number of threads is much larger, right? So a multi-threaded operating system can have multiple threads within a single process. So the Java virtual machine is a process, and it has its own threads. So for example, it has its own thread manager. So for example, here's an alarm clock that's running in a Java thread on the Java virtual machine, which is a separate task. So Java can have thousands and thousands of threads that are all within the virtual machine, and you can control them. And that's a very good if you're planning on doing a web server where you're expecting many people to come and hit your machine. You don't want to start a separate task every time someone comes to your machine, because if you did that, your machine would be crippled. And that's the way things used to be when Visual Basic first came out. Visual Basic did not have a fast threading system. So every time somebody came to a VB-based web page, it created a new task and it would bring Windows to its knees. And that's nasty. I mean, you don't want to do that if you can avoid it. So that's why you use threads. They have a very low overhead context switch. This is my simulation of an LED clock. It's just kind of silly, I suppose, but there it is. And you can see it's running in a separate thread. And in fact, you can see the Java virtual machine over here in the lower right corner. It's a separate task, and it has a series of windows, each of which runs in its own thread. And the window manager also has a thread. So when we look at damage control, for example, this is overriding that, right? But the damage is such that it can, using the AWT, automatically update the pixels in the background so that things can look as though you have one window on top of another. You see? So the AWT damage control manager is running in a separate thread as well. And that's all being handled within the virtual machine. So when we go to create a new thread, here's one, I guess. You can kind of see that what we've got is a run method. And here's the thread target. And my thread implements runnable. There's a few ways you can run a thread. One is you can implement runnable. Another is you can simply pass a runnable object into the thread instance. So let's just try one. I'm going to make a new thread. And we'll call this thread test. Okay. Oh, already exists. I better come up with a better name. I wonder what thread test is. Oh, here it is. Thread test. Oh, this is a complicated thread. How about we do another new one? We'll do a Java class in here. And what we'll do is lambda thread test. So what we'll do is we'll use a lambda expression to create our thread. And so in the lambda expression, what we'll do is we'll say thread T equals new thread. Now we could make a new runnable in here. And in fact, that's what I will do. So I'll make new runnable and then provide a run method. And in that run method, I'll write hello world. And let's format this nicely. And we'll put in a semicolon. And then what we'll do is we'll run it by doing t.start. Or you could do t.run, that'll run it in the same thread. T.start will make it ready to run, and then if there's time, it'll actually run it. So let's see if it'll run. Yeah, so it did. So t.start ran, and that's fine. Now let's try and do another thread. This time we'll use a lambda expression. So we'll make a new thread. Equals new thread. And now, because we know we're going to be passing in something that's runnable, what we'll do is we'll put in null arguments, throw in the lambda expression, and then write s out hello world. Let's see if we can put in a carriage return to make it nice. Oh, maybe I can do this. That's better. You can see it now. So check it out. Because Java knows you're going to be passing in a runnable, just like we did over in here, instead of using an anonymous inner class by calling new runnable, you can use the functional interface lambda, which will pass in the runnable. And then when you call t2.run, well, t2.start, what we'll do is we'll say hello lambda. So that's a little bit different, right? Why? Because what we've done in here is we put in a single line lambda expression instead of an anonymous inner class. Then this works because you have a functional interface and because Java knows that you're going to be passing a runnable instance into the argument of the thread constructor. And you can see they both ran. So now what we have done here is we've introduced two basic concepts. First is the threading concept. And actually, we also introduced, you probably already know this, the anonymous inner class. And then we introduced lambda expressions, which might be new for you. And this lambda expression only works in JDK 8, Java 8. So if you were to refactor this and introduce a variable, you can see that yes, indeed, it is of type runnable. Java inferred that because it knew that thread needed a runnable instance to be passed in. So the Lambda expression essentially saved you from having to write new runnable, which you can look at separately if you do a refactor and introduce a variable. Let's call it R2. So now you can see R2 is runnable, and you can also see the Lambda expression is runnable. And in fact, runnable is a functional interface. And we know it's a functional interface because it only has a single argument. And so it's obvious to the Java runtime that run is being implemented, and that it is of runnable type. How's that grab you? Who got lost? Are Lambda expressions new for you?
Yes.
Okay, so that's a lot, and so maybe I'll refrain from using them for now. Lambda expressions are new as of JDK 8. You could not do this prior to JDK 8. So if you do it, then you can't go back unless you rewrite your code. That's a new language feature. Meanwhile, the anonymous inner class still works fine. And in fact, if you think about it, Lambda expressions really didn't add very much, but they changed the language in a material way. They allow you to declare functions, and that functional interface is a little bit different than the one where you make a new instance of a runnable. So that's an interesting point about threading. Threading is threading new to you as well?
Like I told you before, like it's been a while, so everything's pretty much kind of new to me.
Okay,
I'm like just kind of like all refreshing. I don't really remember that much because I took it like freshman year, first semester. That's a long time ago.
got it. So what I would say is this: if you're going to do any kind of network programming, it's kind of important that you do threading because sometimes you become very I/O bound. And when I say that, what I mean is when you initiate a request for data from a website, the the protocol is a stop and wait protocol. What that means is you issue a GET request, you look for data, you send that request across the network. At the back end, the web browser, the web server, and maybe even some back end data in the web server has to be generated. And then once that's finished, you have to get an answer back. So that takes time. So during the stop and wait protocol, you stop and you have essentially zero throughput as you move your data from one place to another. And so you need to have that running in the background as a thread if you're going to do productive data mining, because you might like to do a second query. So for example, if you said to me, well, I really want to get data on, I don't know, make up a number, 700 stocks. Well, you don't want to do that one stock at a time and wait for each stock. You want to try and see if you can, parallelize this a little bit by doing it in a threaded fashion. So the threading is kind of an important thing for data mining. And I think you guys are going to need it. Let's see now. Let's see, get some more examples in here. Yeah, I don't know if this is a very good example. Let's see if we can't make a little bit of an example. This is the Lambda thread. Let's do another one. New Java class. I'm going to call this thread stress test. And in my threads test, what I will do is I'll put in a main method, and I'm going to make I think I'll make a lot of threads. I don't know. Maybe we'll create something like a thread array. So in that thread array, I'll put in, I don't know. Let's start with 100 threads. And then we'll loop around. And maybe what we'll do is we'll make this an int. There we go. So now what we'll do is TA of I will be the ith thread, and that will be equal to a new thread, new public void run, and then we'll do s out hello, and then did I miss a? I think I've missed a parenthesis, huh? Oh, new runnable. There we go. Now let's take the print and we'll throw it in, and then we'll take the extra parenthesis, and there we go. Do people see what I just did here? So I made my runnable, passed it in, gave it a run method so the thread knew how to run itself. And then what we'll do is, I guess we'll start the thread, TA of I dot start. Maybe the thing to do over in here would be to print something here that shows it's unique. Let's print new date. And for the date, we'll use Java util date. So that's been imported. I think this will run. Let's just see. So that's 100 threads. And there they go. So making 100 threads is not a problem. What if we wanted to make 1,000 threads? Not a problem. Now, what if we wanted to make 10,000 threads? Well, I don't know if I have enough memory for that, but let's find out. Wow. So he did it. And he ran. And it did it. And that's it. So if you want to do a lot of threads, you can. And probably these threads were pretty trivial. They just ran and then they died. So when we look at the thread life cycle, threads are born, right? Threads become ready to run when we hit start. The thread scheduler will allocate some resources, that's time and space, and then it will run the thread. And once the thread's finished, once the run method exits, the thread is killed and it's reclaimed by the garbage collector. So what happened here is we didn't have 10,000 threads at the same time. The threads were executing and dying very quickly. Because if I had to have 10,000 threads all running at the same time doing some substantial work, I would run out of space and my system would be brought to its knees. So what we have here is a nice flexible way to create lots of shared memory objects, and every thread shares memory with every other thread. And that's why we say that threads have a low overhead context switch in comparison to tasks, which have protected memory, but we pay for that. We pay for that because we really don't have very much memory, and they're not, the tasks aren't sharing memory. So when I go to About This Mac, the total amount of memory I have is the hard-coded memory, 16 gig, plus any virtual memory that I might have. So that's a bit of a problem, right? Because if you think about it, I can't really allocate more resources than is available to me. So when we look at something like the Java compiler and we look under preferences and we see, how much memory is being used by the heap, we have very limited resources for that. And in fact, we run out of memory on our heap. So when you type in heap, I think it will show you under the compiler. Yeah, I've allocated 2.7 gigabytes to the heap. I mean, that actually helps me a lot when I go to do the compilation, because otherwise things get very slow. So if you don't have enough RAM, your compilation will be very slow, and it'll show, right? So that's why I'm able to get things to run so quickly. Is it making sense? Am I?
It makes sense. Would this be considered like a daemon thread? Because, or no?
Yeah, you can change the daemonness of the thread. So to answer the question, TA of I dot set daemon, make that true. Okay. Now it's a daemon thread. So now if you take a look, marks the thread as a daemon or user thread. Java Virtual Machine exits when the only threads running are all daemon threads. The method must be invoked before the thread is started. So now he says if it's alive and daemon is on, the virtual machine will exit if the main thread of execution exits. So these may not run to completion if I set everything to be daemon. Let's see. Oh, it seems to be running anyway. Let's, as an experiment, let's set it equal to false. I'm pretty sure we got 10,000 threads coming out. Let's set it to false and see what happens. I don't play with this often enough, so it's a good question. Let's see. Well, I'm a little bit surprised. I think the daemon threads are going to exit, but it takes a while to start the threads. So we don't really know how many threads have executed here. We should have a counter in here that keeps track. I guess I think you can print out I, but you may have to declare it as final. So this is a problem. Let's see what happens inside of an anonymous inner class when you do something like this. I colon plus. I don't think he's going to let me do this. Yeah, he is unhappy. so if you copy it to a local variable, you can do that. Now here it says integer final I. So he made it local, made a copy. I goes in here, threw it into runnable. So he's liking it. You see, it's very interesting. He'll make a copy, and each time he does it, it'll be a different copy. Let's see if he can do it. I think he'll keep track of the. It's supposed to go to 10,000 threads here. Is he skipping? I think he's done them all. He did all 10,000 threads. And he did them in order. That's pretty cool. It's pretty cool. Let's assume for the moment that I want. This is I'm shooting myself in the foot here. Let's do 100,000 threads, because what the hell? I can't believe it's going to run, but I don't know. It may be running so fast that it starts the thread and then ends it before the next thread has to go. I don't think these things normally can keep 100,000 threads resident all at the same time. But starting threads that end quickly returns them to the heap. Because otherwise, I would not expect this to work. But here we are. We've created 30,000 threads already. I mean, this thing is doing great. But you can see what happened. I started each thread as I went. Now, if I didn't start the threads as I went, if instead what I did was I ran a separate for loop after creating all the threads, I don't know. Is this too tedious by half? Is this interesting? I'm going to take this start method. I'm really going to try and press my luck. So now I've created all the threads first. Then I'm going to go through and start them. That means they're all going to be instanced first. I can't imagine I have enough memory for this. Let's try it. Whoa. Well, that's amazing. I'm very impressed that this thing is working. But that's cool. I'm going to stop it now because it's taking too long. But it's fun. I mean, you guys have the opportunity now to do multi-threaded programming. It feels parallel, but it's not unless you have multiple cores, in which case you can have real parallelism. Or if you have distributed computing, which is another topic which we can address in this course. So how am I doing with the threads here? Are people kind of good with threads? I can give you the PowerPoint death march, but I don't know if you want it.
You could if you want, but I'm slowly understanding it a lot better.
Yeah,
Okay.
you can cover it.
You want the PowerPoint death march? Huh? Okay. You got it. I mean, I kind of think maybe it's tedious, but I'm happy to do it.
You could also just like go through it pretty briefly. You don't have to go.
You know
through
what?
some
I
depth.
that's what I'll do. That's a good idea. I'll try and keep it short because I don't think you want to see the whole thing. How many slides is it? I don't even know. I'm getting this spinning beach ball of death as I try and bring up the PowerPoint. let's see what's going on here. Oh, it's working. It's working. It may be Zoom slowing me down. I have the recording going on the iPad, and things seem a little bit faster as a result. So there are 38 slides here. We understand what multitasking is now. This is when you have, what we call protected memory. A true concurrency is when you're doing two things at the same time, multiprocessor systems, like what we mostly have now. These are truly concurrent systems. So when you look at, my system here, you can kind of see that there's a lot of different things going on. What is this? A bunch of different things are running at the same time. Networking is happening. The CPU is being used. A lot of different things. Now, CPU threads are really different from the threads that are in a Java virtual machine, right? Because what happens there is if you have a hyper-threaded system, like in, I think they call it something else under AMD, but in Intel, they call it hyper-threading. It's like you have two hands and you're chewing your feet. Like if you have a bowl of popcorn and you have two hands, one hand goes in, gets the popcorn, puts it in the mouth, while the other hand goes out to the bowl and gets another kernel of popcorn, and you just keep switching from one hand to the other. That's a way in which you can do hyper-threading. So one CPU core can have two threads feeding it, making sure that it's always being kept busy. The threading in the virtual machine is rather different. Here you're actually creating several different low overhead processes, and they're running at the same time. Through a scheduler. So the scheduler will switch from one to the other, but that's not true concurrency. When you look at the Flynn taxonomy, there's SysD, SIMD, MISD, and MIMD. SysD, single instruction, single data. SIMD is single instruction, multiple data. So we call that vector computing. And you can see that for the instruction set. So for example, you used to see MMX on the Pentium processors. That MMX was multimedia extensions. That was a SIMD extension. When you looked at PowerPC from, was IBM and also Motorola, they had AltiVec, which was another vector machine. Think about it this way. A plus B equals C, where A, B, and C are arrays, homogeneous arrays, and A plus B is being done in one CPU cycle. So in a single clock cycle. And then all of that stuff has been jammed in to a bit of memory called the vector processing unit. And it gives you an answer in parallel as an output, which can then be stashed into memory with a virtual memory address unit. So this stuff is being done so that it can offload from the SysD machine, the main CPU, some of the work. So for multimedia work, that's great. SSE, that's the streaming SIMD extensions. There's SSE2, that's the extensions that were added to Pentium after MMX. So we had MMX, SSE, SSE2, all of that's SIMD. You go out to NVIDIA and you start using the CUDA cores. Each one of the CUDA cores has a SIMD coprocessor built in. So it's a way in which you can do your programming. It's not particularly easy, but it allows you to do a little bit of, I will call it parallelism. MISD, that's when you have multiple instructions, single data, and you can create specialty architectures for that. We don't see that very often. MIMD, that's when you have multiple instruction, multiple data. That's when you have, like, say, a network of workstations. So if you have a network of workstations, each workstation could, for example, work on a different frame from your movie. And then they don't have to talk to one another very much, except when they're done with the frame, in which case they can number the frame, and drop it into the file system. And so if every frame takes a half an hour to compute, it's not going to be likely that it will be IO bound. And you could add 10 computers and go 10 times faster, that sort of thing. However, if you become IO bound, 10 computers do not make you 10 times faster. When you become IO bound, your ideal speed up is when you get 10 computers that make you 10 times faster, but your real speed up is when you add 10 computers, but you're only going 2.5 or 3 times faster. And that's because you've got the overhead of communication. So the multi-threading systems, we already talked a little bit about them. They enable us to have what we call a low overhead context switch. So that means you don't have your protected memory. And so that means all the threads have to play nice with one another. They share memory and they can step on each other's toes. So you have a powerful gun. Don't shoot yourself in the foot with it. If you have a protected memory system and let's say Photoshop crashes, hopefully the rest of the operating system does not crash. You need a task scheduler for threading. You need a task scheduler for multitasking. So when you look at something like this, you can see there is a task scheduler here. When you look at something like, here's Indicia. I'm going to kill this job. Are you sure you want to kill it? Yeah, I'm going to force quit. So now Indicia dies, but nothing else is impacted. Indicia is just in case you're wondering, it's a thing that helps you to make stamps. So at some level, it's not a critical thing to the operating system. It's just an app that somebody installed. I guess I did. And it enables you to get certain features like the ability to print stamps. So that's not a, particularly difficult thing to envision. Here comes the activity monitor. Now it looks to me like it has a process ID. So now if we look at, I don't want to force quit. Let's just close this. If we look at processes, right, you can see there's a bunch of them. And then if you look at the ones that are for me, you can see, well, look, there's a process here that has an ID and it has a priority. And if you want to, you can renice the process ID so it gives it a lower priority. And then when you look at your total load, you can see, oh, there's 279 processes. My load is pretty high. I've got, a CPU mostly idle here. You can see the physical memory being used. This is what happens in a true multitasking operating system. Here's another multitasking operating system. So now this one is a Raspberry Pi. And he too has 237 tasks. I guess everybody has a lot of tasks, but he's 98% idle. You can see it right in through here. And if you wanted to, you could see how you could do a little data mining. Let's do, here we'll do some data mining from Yahoo. And we'll look at Apple. So what this is going to do is it's going to give us what we'll call financial features, right, from Apple, which will be available to us by virtue of our going out to the web and getting the data from a source like Yahoo Finance. And here we can see we have like 8% growth, and we can take this number, right? If we wanted to, we can go in to a live Excel spreadsheet. Let's try looking for Microsoft 365. Microsoft, I don't know if you know about Excel, but Excel has been placed on the web and given formulas that allow it to do data mining on the web, including financial data mining, which is kind of cool, but it's very limited. So we can supplement it with data that we obtain from other sources, such as Yahoo Finance. Oh, this is terribly slow. And we're back. So now the data that is being shown here, let's go and take a look at Apple. Find AAL. Paste that in, that updated some of the data here. And we can see things like the 52-week low. These are formulas that are coming right out of Excel. So Excel is able to do live financial data mining. And in fact, if we click on the link in here, we can see there's a whole bunch of different things like the number of employees at Apple, that sort of thing, that you can get directly from the Microsoft Excel website. So if I said, gee, I wonder how many employees there are at Apple, I can add that. And it says here there's 164,000 employees. So he can go out and get data that would otherwise take you a little time. Like, I'm not even sure how I would go and get a reliable number for the number of employees working at Apple. And I had no idea it was 164,000. So from that point of view, there are things that you can derive as raw data and other things which you can compute. So for example, here is the market cap over $1 billion. So I can get, numbers like 2,431 billion. So that's $2.4 trillion market cap. Wow. World's most valuable company. Here I can compute intrinsic value of the firm by looking at cash flows and discounting them over the next 5 years based on projected growth of 8%. Herein lies, a question of how you value a company. Here I subtract off the debt that the company has, which is $111 billion from, and add to it its cash, which is like $51 billion. And then I look at the intrinsic value of the growth of the company, and then I look at the market cap and form a ratio, which is the owner's equity divided by the market cap. And it's not all that great. It's looking a little overvalued. Whereas Taiwan Semiconductor is a different story. It's quite undervalued, but we have to take into consideration the so-called geopolitical risk, because something bad might happen to Taiwan. We don't know. And so that's why it gets discounted so heavily. So therein lies the rub. We have a mixture of what I would call live data, which can be fed in, things like the price, and derived data, things that we compute. And then we have semi-static data, stuff that we have to go out onto the web and grab with our Java program. And you can imagine if you're doing a lot of this grabbing of financial data from Java, you need threads for this, right? Because check it out. If I said to you, well, let's just take a look. I'm going to do Apple and Intel, and I'll do Lyondell Basel, and I'll do Cowen, and then I think maybe I'll do Rogers. That's not that many stocks, right? There's 1, 2, 3, 4, 5 stocks. How long does each one take when it's running one stock at a time instead of doing it threaded? And the answer is, it takes a long time. And so you don't do this very often, right? I mean, look how many seconds per thing this takes. I mean, this is terribly slow. So you would like this to be multi-threaded, but it's not right at the moment. And so from my point of view, it's an obvious application of threading. You want something like this to go out and do some threading. Now, someone said, John, was it you? I forget. You had a question at the beginning of the class. Will there be a project for this class? And
Correct.
the answer is I would like that. And I think you guys would too. But for now, we're just trying to catch up in terms of getting everybody up to speed with a little bit of Java background. So let's get back to the PowerPoint. Task scheduler allows you to change your priority. It does a round robin scheduling based on the priority. Tasks with higher priority get more resources.
Professor, is this code all in the Intel that we uploaded the first day or the second day? Course?
Yep, all of this is in there.
Okay.
Yeah, so if you wanted to mess around with chapter 13, you will see there is something here called book examples. And I got code for each chapter here. So I got the nested reference data types, packages, exceptions. I did a thing for arrays and vectors. I don't think I want to get distracted by that. I could go on and on with this stuff. But anyway, let's try and get through some of this. I'm going to go quick if that's okay. So you guys tell me if I'm going too fast, okay? The multiprocessor systems typically will give you a hyper-threaded experience where the hardware is attempting to keep itself busy by using two threads to do the I/O. And so he will do a request and overlap that request with a little computation while he does another request. And so the prefetching goes into what you call a cache, and this is done through direct memory access and a virtual memory address coprocessor. So that's typically what happens in the hardware. But you guys, don't have to worry about things like memory swaps and high overhead context switching if you stick to Java threads, because those things are not needed because we don't have protected memory. What will happen if you use too much time swapping in from the disk into your high-speed memory is you will end up thrashing. And if you had a mechanical drive, you'd see a light blinking and you'd hear it ticking and you wouldn't be making good progress. That's a big problem. So when you think about it, mechanical drives might have millisecond access time, maybe 10 milliseconds, whereas RAM could have nanosecond access time, like maybe 10 nanoseconds. And a nanosecond is 1 times 10 to the minus 9. And a millisecond is 1 times 10 to the minus 3. And 3 minus 9 is like 6. So your RAM is 1,000,000 times faster than your hard drive, especially if it's a mechanical hard drive. But even if it's an SSD, if it's running over USB 3 or something like this, or USB, I don't know what the next generation is, 4, it's still way slow compared with the RAM that's co-resident with the CPU. So our threads will all share memory. It's a very good, I'll call it a speed hack for doing things that look like they're happening concurrently, but really aren't. They're simulating concurrency. Deadlock, that will happen when there is no progress that can be made because of a consumed resource. So for example, I can't have 2 threads write to the same file at the same time. The file's open for write and you haven't released the file. The other threads that need it can't use it. That's a problem. That's deadlock. A threaded pipeline enables you to have one thing feed something else. Now, that can be done in simulation. So for example, LS, I can pipe it into WC, and then I can say -L, and this will tell me there's 31 files in this directory. So WC does a word count, counts the number of lines. LS lists the files. So the output of one thing was fed into the input of the other thing. That's what you'd call a static partitioning of the tasks. Now you can do static partitioning of tasks and still get good throughput, but what's really happening there is you are making a pipeline. And that pipeline has to, in some sense, have a reasonably good partition, or else what'll happen is one thing will hold up everything else. So for example, if you told me I need to make electric pickup trucks at GM, or maybe Ford. Ford makes the Ford Lightning, right? That's a great Ford F-150 is an electric car now, or at least there's an electric version of it. So now they can't make them because supply chain issue, right? So everything gets held up because they don't have CPUs or some stupid ass thing like that. And so then you're like, well, my whole car company has to shut down because I don't have a part. And the answer is yes. It's in the pipeline and it's in the critical path. That's a data flow pipeline for you. So as one thing flows to the next in an assembly line, if you are missing stuff, you're screwed. You don't get good productivity. Same thing happens in agriculture. You have to have your inputs. They have to be there on time. You need your sun, you need your water, you need your fertilizer. If you don't have all three, then you got to wait till next season because you can't have a harvest. Right? And that next season could be like a year. That's a big problem. So we've seen me give you examples of thread T equals new thread. Runnable is an interface that takes a single method called run. It's a functional interface. That's just one function, returns void, and is called for its side effect. And runnable is there because you want an inversion of control. Every thread knows how to run itself, and it doesn't know what it is you want to run, so you have to provide the runnable method for it. Here's the life cycle of the threads. Threads are born, new thread. Threads are said to start. That makes them ready to run, but they're not running. T.run is called by the thread scheduler, at which point they are running. Once they are returning from the run method, then they are said to be dead and they return to the heap. And I think you saw me make like, I don't know, 10,000 threads. If it is IO bound, it will be blocked, but that's going to yield time to the other threads. So if what you're doing is you're going out and waiting for Yahoo Finance to do a computation and return some financial data, turns out it's blocked, which means the other threads will have a chance to run, which is really very good. So here it is again. You can call thread.sleep in order to be really nice about getting the thread to let other things run. So if you wanted to, you could start the threads at random times. So you could do thread.sleep and maybe math utils dot get random number from 0 to 255 and maybe multiply it by 10, and then thread.sleep, that can throw an exception. So we'll surround it with a try-catch block. And so now they'll all sleep for random intervals from 0 to 255. I don't want seconds, but maybe a couple seconds, I guess is right. Let's just do this. I guess that'll work. And then how many of these do we want, really? I think 1,000 threads is enough for this example. I don't want this thing to run forever. It takes too long. You could see thread.sleep is working. This thing is taking too long. Let's stop it. So when you have a sleep in there, it gives the other threads a chance to run. The garbage collector runs in a thread. And in fact, you can turn off the garbage collector, but it's quite dangerous to do that because you could run out of memory. But garbage collectors typically wake up and start to collect garbage in an asynchronous fashion. So if you want real-time control, you may actually want to turn off the garbage collector. There's a system thread group, and you can group the threads, renice the threads, that is, change their priority, and change their names. And so it's a deep topic in Java. There's a lot of information about threads. And I think you saw a few of these already. And we talked a little bit about daemons. And deadlock occurs when you have issues. Here comes my project, Project Empyrean, which is described in one of the papers that I cited at the beginning of this last homework. And that's the one where all the run jobs provide a run method, and then that run method is invoked for you, and you have a high-level interface to the threading. So here we are running every 1.5 seconds. We're not a daemon, and we run 5 times. And this is the UML for that. And UML, I don't know if you guys are familiar with UML, but runnable is an interface, run job implements the interface, thread implements the interface, and then this is a symbol for composition for the run job command thread, and that subclass is the thread class. So that's what UML does. It's giving you a pictorial view of the classes and their associations or relationships. So that's what I've got here for threading. Was that too much? You guys awake over there? I can't tell.
Yeah, no, I think that was good.
All right. So you
Oh,
got,
yeah.
good. You know, if I'm going overboard with this stuff, you got to tell me because I can't see your faces and I don't know if you're falling asleep over there.
I just have one question. So you're
Sure.
only manually putting the threads to sleep just to wake up the other ones or to have more control? What's the purpose
Yeah.
of putting this threads
Yeah.
to sleep?
So if you're playing nice with your neighbors, you don't want to hog all the resources. So what you want to do when you're doing sharing is you want to define what sharing means. Sharing means different things to different people. Like if you're doing something that's really time critical, maybe you don't want to share very much. Maybe what you really want to do if you're doing sharing is you're saying, I'm going to get some and then you can have some. And after you've gotten, through a couple or 3 queries, you're going to yield and let somebody else run so that your system doesn't seem like it's bogging down. So if you have a graphic user interface and you want it to run and you want it to look nice, you might like it so that you yield a lot so that trivial turnaround time for the user is good. Because if your graphic user interface looks sloppy and slow and you click on a button and it's like, watch it turn slow. I mean, watch it turn color slow. You may not like that. So to give your users a good, I'll call it experience with your code, yielding is a really important thing to be doing. So having threads that yield, I mean, so far everything I've done has been pretty trivial. But if I had a thread that had a run method that took a while, not just printed out something and then died, that might be a thing that you would like to yield on occasionally. So that's that. Let's see.
And one more question, sorry.
Sure, no worries. Don't be sorry.
Now, the random, would it be faster if you like, I don't know how to tell or show this without like drawing it out. Would it be faster if you like staircased it, the threads, instead of randomized? So like, let's say you had threads 1, 2, 3, 4, just for example, and then you had thread 1 running the longest, thread 2 is a little shorter, 3 is a little shorter, 4 is a little shorter, and then like once process 1 wore down a little bit, then 2 starts, then 3, then 4. Do you get what I'm kind of saying?
Yeah, I mean, there's all kinds of things you could do. Like here's this sort of data mining thing, right? I just went out and I got a list of companies. I'd like to get information about each one of those companies. Now, I could probably do that all at once, but it could take time. So if you said to me, well, getting information about each company takes time, I might like to go out and do several queries at the same time and hit this finviz.com website simultaneously from, 2 or 10 different threads. But the danger of doing that is that it may see it as a denial of service attack and block my IP address. If that happens, then I'm screwed. I have to wait until, I don't know, they either whitelist the IP address or if they have to request it with an email or something like this. It might be really good for me to slow down the queries with a sleep method. So the sleep method's not just for your threads, it's for the websites you're going to use in order to do your data mining. So you might say, you know what? I really don't want to hit finviz.com 100 times per minute, right? Maybe, if I do that and they block me, I'm screwed for the next 24 hours. So what you do is you throw a thread.sleep in there and maybe you throttle your rate, your query rate down to, let's say, once every 10 seconds. Maybe that's what it tolerates. If you're going faster than that, it thinks you're a machine and not a human. See, that's really important. So that's the kind of thing I would kind of use sleep for. And you can see that happening not just from finviz.com. There's a lot of websites, they really don't like it if you go in there as a Java programmer and do your data mining. They just don't like that because they think you're just stealing their data, which you are. I mean, it's their data. And so at some level, you might need that thread.sleep. That might be a really important thing. Let's see if I can give you another good example here.
Yeah, I think I understand it now.
Yeah. So here we go. This is a data mining program that I was working on, and I think this URL is going to work. So let me go out and just test it first before I demo it. Okay, so here's all this interesting data that I would like to get from Apple. And there's the company and the market cap. And then he gave me a pop-up with some kind of an advertisement because I don't pay for this stuff, which he really wants me to do. So what I'll do is I'll claim that what I would really like to do is take the data and parse it and populate a data structure. So let's have a look at this is CSV data coming back. Let's run it and see what happens. A little bit slow. Okay, so he came back with something. Here's the header. That came right off of the website. His market cap, apparently it's in billions. This data has got the look and feel of something that may not have been properly parsed. And you can kind of see, like, here's a number, right? What the heck is that? Line 20 has 15.89b. How do I parse that, 15.89b? That's not easy to parse, right? I mean, what is that? What happens if it's m and not b, right? Is it billions? Is it millions? Is it thousands? Maybe that'll be a k. So what I've done when you look at this code is I populated it by doing get Yahoo integer 2, right? So this right and through here is in fact, I think I got it in here twice because I was just working on it today. This will allow you to take, something with a B in it and turn it into billions. So that's a kind of a parsing program that's built in to the string utils, which I've distributed to you. So here you can see if it has, B's or M's or K's, it'll turn it into billions or millions or thousands, or T's for trillions if it says trillions. And then if it's a trillion, it multiplies by 10 to the 12. If it's a billion, it's 10 to the 9. If it's a million, it's 10 to the 6. If it's a kilo, it's 10 to the 3. If it sees a percentage, it turns it into a percentage thing. And he can parse the float. But you see, if you call float.parse float on something that says 10 with a percentage sign, that's going to choke. So you've got to be a little bit more careful about it and start replacing things that are, indicators of quantity, like millions, billions, trillions, and thousands, and multiply accordingly, or else you're going to have issues with your parser. Float.parse won't be able to handle numbers like 12b. It doesn't know from 12b. 12b, what could that be? I don't know, B. So it's like, running everything into Yahoo int 2 will actually help you when you go to do something like set your market cap. So that's it's a little bit tricky to do things like that, but you kind of have to when you're doing things like setting the number of shares outstanding. And the other thing you have to do, and this is sort of important, is you have to know what column the data is in. So when you go and you print out the CSV data, you'll see that I've actually numbered each one of the columns as they come out. That's how I know it's SA of 14, because if you look at SA of 14, you'll see a number that looks like the size of Apple in billions or something like this. So here's SA of 14. And here you can see this number here. That's not going to parse easily. And you might wonder, what comes after the company name, and it's the market cap. So it's a big number. The next one is the forward PE, right? So if you were going to try and parse that coming off of this array, it would be something like F dot set forward PE, and then SA of, and I think the next one is 14. But you can see how manual that is. Now, oh, here it is. It's 15. 15. And now you've got to go and you've got to parse that guy. He's a string. Maybe float.parse will work here. I don't know, but you can try it. And then if it doesn't work, you'll get an arithmetic error exception at runtime, at which point you may have to take into account some oddball string that's contained in the in the input data. That actually might have worked. You see, he came in with 23.34. So that actually worked. He got a forward PE. And in fact, there it is, 23.34 forward PE. So that's cool, right? I mean, and he got the market cap at 24.29 billion. So if you go back and you take a look, you might actually be able to find it. Okay, here it is in scientific notation. The numbers, I don't know what to say. I would say it's astronomical, but astronomical numbers are small compared with these. These are, it's $2.4 trillion. This is a big number. So there it is. I mean, you're getting an opportunity now to do real, get a little insight into some real financial data mining, which is kind of cool, actually. So that's that covers a lot of information for you guys. In fact, what we ought to do is take a look at the next homework assignment, which is homework number 5. So if that's all right with you guys, I'm going to get out of this code and take a look at your next homework assignment and see if there's anything in there that you might like to have me review before you have to deal with it. Blackboard is getting really slow. Or maybe it's my computer. So this is your next homework assignment, homework 5, chapter 18. It's on swing. And you got a bunch of videos here, and some of them are on layout. And I think we talked a little bit about the run methods for runnable jobs. I have the same sort of thing available for the command design pattern in swing. So I have buttons that know how to run themselves. And that's kind of an interesting thing. So you've got runnable everything. The whole AWT has been rewritten so that things know how to run themselves, which is quite interesting and a little bit different than what you might be used to. But here is, sort of information about painting and how you can fill rectangles and draw lines. And I think you may have heard me talk a little bit about the AWT Damage Control Manager. That runs a thread, and it schedules a repaint invocation when damage is detected. It updates areas as well. Let's see, what else do we have? A lot of this is obtained by reading the book. Let me see, fill in the blanks, drawing a frame. Maybe what we'll do is a quick overview of swing. That might be of some help for you guys. Let me just see what else we have in here. Checkboxes, frames. Oh, lambda expressions. I think you saw me use a lambda expression. Let's see now. I think that's it. Let's go back into chapter 18. Take a look. What do we got here? 52 slides. God, that's a lot. I don't know if I'm going to want to torture you guys with 52 slides. So Swing is a graphic user interface that's built on AWT. AWT gives you access to a uniform API as you go from one platform to the other, but its look and feel is different. So as you move from one AWT, it will look like X Windows. When you're on X, it'll look like Microsoft Foundation Class Library. When you're on Windows, it's going to look like a Mac when you're on a Mac. Swing will look the same on every platform. Do you guys need a review of Swing?
I have no idea what swing is even.
All right, so Swing is, yeah, Swing is the graphic user interface that Java provides so that people are able to do GUI type programming. So it's the way in which you create a button or a label or a panel, table or a tree, a frame.
So is it
it-
like a user interface type of thing?
Exactly. It'll give
Okay.
you all the buttons and the input dialog boxes and all this other stuff. Here's a combo box. Anything that begins with a J is all part of the Swing API. I have my own versions of these things, like the progress bar. I'll have a run progress bar. Panels.
That had bread, and that's the only reason she's making like 40 a year. She makes about 1,500 probably like a week.
And that's not bad.
That's not bad.
Josh,
No,
Mike, Josh, Mike.
Oh, sorry about that.
Yeah. Sorry. Yeah. That's it. So at some level, I think you're not doing any graphic user interface programming if you don't know AWT or Swing. And I started everything with AWT, which is the Abstract Window Toolkit. And then I moved over to Swing, but I kept both just in case I wanted to go back. And so, for example, here's the J button. What I did was I created a run button that allows you to create buttons that know how to run themselves. So when you go into the GUI package and you look for the run package, you'll see that there's a whole bunch of run components. And one of them is called the run button. And so in the run button, I'll give you an example where things are working. Here's a closable J frame, and I put in flow layout, and here comes a run button. When you click it, start will press OK button. And so the start button knows how to run itself. And you could write in here, start. And now when you run the program, you should see a button that says start. The one that's, this is a start button that's using Lambda expression. Let's see if we can get things. Oh, this was commented out. I didn't even notice that. Just at the last minute, I saw it was commented out. Let's see if it works. Yep. So here's the start button and the stop button. And they know how to run themselves. Now this one has been commented out. Let's. There. This is run button 2. Is there already a run button 2? I guess there is. Or not. Oh, he's all right with it. Okay, let's run. I think we lost Selena. Well, this button has not been added. So let's add that button. So now with flow layout, we'll see the buttons go as run button 2, run button, and then stop. And we'll call this something like run button 2. And we'll call this one RB. And you might notice the little bracket in here that enables you to hit Alt-R or Alt-S to get a shortcut in there so that you can run the buttons with your keyboard shortcuts. And that's a feature I built into the run buttons. So there should be 3 buttons here, and there they are. Now if I hit Alt, yeah, you can see it. When I hit Alt S, doesn't look like it picked it up for some reason. So that's the run buttons. They know how to run themselves. The run method is associated with the button, and then the button gets added to a container. And then the container has to have some sort of a layout associated with it. Here's a flow layout. Let's do a different one. Let's make a grid layout. And we'll make it 2 by 2. And let's see if we can get that to work. That should change the look and feel of the buttons so that there are 2 rows and 2 columns. But I think there's only 3 buttons, so I'm not sure how that's going to look. Oh, he's giving me this spinning beach ball of death. Yeah, that kind of looks crummy. But there are 3 buttons in a 4 by 4 layout or 2 by 2 layout. So there's room for an extra button. That's the sort of thing you might like if you were going to have something like a dial pad. Here's a dial pad. And so if you said to me, oh, I have to dial 1-800-MATTRES, leave off the last S for savings, I think I can convert that to numbers. That's the letter to number thing in my dial pad. So you can see this is a grid layout. It's 3 columns by 1, 2, 3, 4 rows. And then there's a separate panel which consists of 1 column and as many buttons as you like. So you can simulate the dial pad of a telephone and include the DTMF, dual tone multiple frequency codes that are built into the telephone system when you're doing plain old telephone service or POTS. So when you're looking at my address book program, for example, you can sort of see that I can dial the phone in more than one way. And so there's a setting in here that enables you to set up the dial so that it can use DTMF. So it'll dial with the speaker and use touch tone instead of dialing with the modem. And when you look at the preferences, dialing with the modem is possible because I have a USB to serial port dongle called Key Serial, and that lets me communicate with the modem and let the modem do the dialing directly. So in principle, I don't know if you can hear this stuff, but this is my dentist. Let's see if I can dial my dentist. I don't think he's going to be answering. I don't know, can you hear it? Maybe you can hear that, I don't know. So it's got the ability to do dialing and that sort of thing, get through complicated voice trees, voice jail, that sort of thing. So you need the graphic user interface if you want to be able to do reasonable programming, I think. I mean, that's sort of an important feature. So what I did was I provided run methods for everything. So here's the run checkbox. Let's see if we can get that to work. And it's giving me the spinning peach ball of death. So here I've put in some icons from pictures, and I can click on these things and they work. Now I think the interesting thing is to see how that actually gets set up. So here it is. We make a closable J frame, get the content frame, the container, and then we add the checkbox. And here you can see where the keyboard shortcut is being built in. Throw in a couple of extra buttons, another run checkbox, get some icons, throw them in there as well. That's my shtick, you know. I think it lets you basically isolate the business logic into a little run method right in through here, and that kind of makes things kind of nice, I think, because otherwise you have to add action listeners to the components, and that can be rather tedious. Let's see if we can get this to run. Sometimes things get a little slow here. If I hit enter, yeah. So the enter is what gave it an action. And the slowness, well, that's just me running Zoom and being slow about it. So the run method is being invoked whenever you hit enter. Then it goes here and gets the text out of the run char field, and then you can do whatever you like with it. And I've got a wide variety of different run methods for you guys to use. So here's a run menu item. Let's see if we have an example. Yeah, there is a main method here. He calls get menu bar. And so the menu bar it's a run menu bar, which gets a file, edit, and category menu. And you can see these things here, right? These are all run menu bars, and this is a hierarchic menu bar. So whenever it pops down and works its way sideways, that's hierarchic menus right in through there. So here's a stock data mining menu. Let's see if we can get this to work. I don't know how slow this will be. Oh, this isn't bad. Here's a J tree, and that's drawing the menu in a tree, which is kind of cool. And in principle, yeah, if you click on it, it says "we." If you click quit, it quits. So it seems to be working. So if you go to the file menu, you can see where everything has been added. And these here, these are mnemonics that are used to control the shortcuts. So from anywhere, you can say Alt-Shift-Y, and that'll do a close. And Alt-Shift-X is supposed to call system exit, which should cause the program to quit. Alt-Control-Delete, you can actually do that on a Mac. It's a funny thing. You can't really do that very easily on Windows. You can't intercept Alt-Control-Delete. So let's see, what else can we say? Swing, they call it a lightweight system. It's built on top of AWT. AWT is using the operating system supplied graphic user interface. So when you get a file dialog box using AWT on a Mac, it looks like a file open dialog box from the Mac. If you're on Windows and you have an AWT file open dialog box, it looks like Microsoft Foundation class library file dialog box. And this is all from chapter 18. There are toolkits that let you do things like get the screen size. It's very important if what you're trying to do is position windows. So for example, I might like to do something where put this to the left, and he knows where the left is. So you can put it up on the left and lay out the screen nicely for me. He knows where he knows the screen resolution, he knows where the upper left is, can position windows for me. So a frame is a component that typically contains panels, and you can organize your graphic user interface in panels and then take the panels and put them in a frame. That's a very typical sort of thing to do. So for example, this is a panel down here at the bottom, and it's got another panel with the dial buttons and another panel with the previous next buttons. Let's try previous, next. The panel with the dial button here should dial. And it does. So when you look at how these things are laid out, what you're really seeing is there's a panel at the bottom that's in the south, panels in the middle, and panel up top. If you bring up a dialog box like print dymo labels, for example, that may or may not actually bring up a, I think I just printed a label actually. It may or may not actually bring up a dialog box, but sometimes these things do. Like this one, set the label font, set the dimensions, dial setup. These all bring up dialog boxes. I sort of think graphic user interface programming is kind of important if you want to write real programs. People like that sort of thing. Here's some UML. This says a JFrame contains a container, and the container contains a component, and the star means it can contain many of them. So what you do to the JFrame is you go and you get the content pane. That container is where you add the components. And there are pros and cons to using AWT. AWT is fast. It's built in and optimized by the operating system. But Swing is portable. Gives you a portable look and feel. Let's see. I don't know if you want to see how to get an int. I think you know how to do that already. Here's a list. There's two kinds of lists, right? There's, well, maybe more than two kinds now. There's the Java util list, which is part of the container collection. And then there's the J list, which is part of the graphic user interface. So when you go into my package here, you should be able to find, yeah, here's a run list. And that extends the J list, implements runnable, so the list knows how to run itself. And there should be an example here. Looks like nothing was saved, but what you can do is you can add, let's add something, IBM, select symbol, IBM. Yep, you got it. Apple, IBM. If I go to IBM and I hit subtract, yep, takes it out. So now if I want to, I can add DVN, Devon. Now I should be able to select that. So the list is a convenient way to have a number of items. Let's see what else we got here. The background on the list is a model. The model allows you to add and remove elements. So there's a model, and then there's a view, and then there's a controller. And the model, that's where you have, you know, the list of things that you can add and remove. The view, that's the JList view. And then the controller, that's when you click on elements in the list and cause an action to occur. There's a thing called the J scroll pane. J scroll pane enables you to scroll the list up and down with a little elevator. That's probably more advanced than you're going to use unless you really get into graphic user interface programming. Let's see. I got a run color chooser in here. That's probably more advanced than what you're going to be using, but I'll show you anyway. Let's see if we can get an example to run. Most of my, if not all of my run components have a test method. Basically, it's a main, public static void main method, which allows you to run everything and see how it can be used. I consider it an important part of the documentation. So here is a, let's see if I can pick something. This should be more green than anything. You can see it's green. You can change the hue, saturation, and luminance, or hue, saturation value, or RGB, or cyan, magenta, yellow, and black. Or just pick out a swatch. This one's red. You can see the red is very red. You can turn down the green, down the blue, make it all red, and then click OK, and he tells you the value. I have a graphic user interface just for doing things like selecting dates and calendars. I think that's a convenient thing to have. So you can add this run date panel, and when somebody picks out a date, it'll call you back and run the run method for you. It's not normally this slow, but there it is. So now what you see here, these are called spinners. So you click up on the spinner and it gives you a change in date. You might like to type something in here instead of clicking on it. So you could probably put in something like 16 and hit enter. And you can see February 16th. Click OK, and it returns the date. So it's nice to have something convenient for being able to do things like set the date. Usage of it is pretty straightforward. I took the run date panel and then I put in this get value and printed it. If you have something that says get an int and somebody types in something that's not an int, you'd like it to detect it and ask the user to try again so you don't get sort of an arithmetic exception at runtime. Same thing for constraints. The file chooser will let you go and select files and gives you directories that you can use. So that gets you into the file IO thing, which is like a whole other topic, which we couldn't talk about, but which is sort of outside of the scope of Swing. So what do you think? Is that enough PowerPoint for one evening?
I think so.
Yeah, I think you guys must be getting burned out. I think we lost Selena. Unfortunately. Sorry about that. She probably got sick of it. So there's that. What I will do, I think, is I'm going to let you guys read the book on up to chapter 18. That'll probably get you through some of the files and streams. Streams are going to be really important for us because we're going to be doing IO on the networks. I had tried to get people to do something with the doodle poll, and I think it was Victor who said he couldn't make it. I think he's a part of this class, right? But he's not here, and he said he couldn't make it in the evening on Thursday, but that's when the class is scheduled. So I couldn't get that. I didn't understand it. I guess there is no regular time for everybody, and Selena's not here, so I can't very well ask. But just out of curiosity, are you guys available in the mornings on a Saturday or a Sunday?
It's honestly 50-50 for that.
I see. All right. Well, then we'll just stick to this Thursday evening. And if I get, I'm getting jammed up because I got a course that I have to go and take. I signed up for a course on Thursday nights, and then I got scheduled for this on a Thursday night. And it's not every Thursday night, but I got a class on.
Could you make a recording possibly?
Yeah,
So
I
that's
think
what I was gonna
Hold
suggest as
sessions
well.
if we have questions. So if you make videos, we could watch the videos, and then if we have questions, maybe we could, if you have every other Thursday available for like an hour, if we have
absolutely.
questions or something
Yeah,
like that,
that's
maybe
exactly
that
right.
could work.
That's the way to go, because if I record it and I think you've got, yeah, like there's a Vimeo lecture here. So if I click on it, will it let you go to the, yeah, so here's the intro to Swing that I just gave you. And so that has all of the same things that I just did, only maybe slower. How long is this? Oh, it's only 15 minutes. So you could probably watch some of these videos. Here's another one. See if it'll take you. I don't know why it keeps telling you this, but if you click on it, it'll take you in. And here it is on events. So now you can get the design patterns, observable, and you can watch these. And so that's good, actually. You've got a lot of videos here. I'm trying to kind of invert the classroom. So you got the buttons, the check boxes, the layouts. Here's the thing on how shortcuts work. So you got a lot of video stuff in here, and there's this paper. Now the paper, I think, is good reading, and it's not too long. It's 14 pages. And so that'll give you a little insight into how the entire system works. And so you can read that and you'll see, this is all screenshots from live code that you have. That's all part of your distribution. So you might like to give that a read. This is an old paper, but it's still good. It's still good. So yeah, the videos are here, and you should be able to watch them. And I honestly didn't think that the $1 a month was a hardship. At least I hope it isn't. So that's that. I've got videos for you guys already, and hopefully you'll be able to watch them. And if it is a hardship in terms of the $1 a month, let me know. And what else? I got any questions for me? Well, I think
No.
that's enough for one evening. I want to thank you all. I think tomorrow is going to be a little bit chilly. I'm going to upload this video presentation for you guys to watch, in case anybody's missed it, like Selena may have missed some of it. And next week, I'm going to try and do something with a recorded video, if that's all right with you guys.
Yeah, sounds good.
Very good. All right. Thanks a bunch. Have a good evening.